could you please start?
Okay. Okay. Thank you very much for introduction. So I really appreciate the organizers for giving me this really great opportunity to talk about the recent advancements about using neural networks to simulate or encode quantum many-body physics. Okay. So I would like to make a short introduction about myself, which would be done very briefly. So I have finished my PhD in 2020 in University of Tokyo at Katsura Group. And I did postdoc research at RIKEN and then moved into University of Tokyo again. And currently I'm working at Sagawa Group in Applied Physics Department. And my interest has been algorithms, all algorithms, I would say, for that could be used to investigate quantum physics. And for example, I have worked on using machine learning to classify the phases in quantum systems, and also it also includes representation of quantum many-body states, which will be the main topic today. And also I have been doing some developments of quantum algorithms that is based on quantum computers. And yeah, so my main interest is in the intersection of these three circles right in the right here, so each of them denoting quantum information or technology, machine learning, and also the quantum physics itself. Okay, so here is the agenda of today's talk. And I have never done a talk of length 3 hours, which would also include short breaks in between. So I'm not sure if we can go through all of them, but let me provide the overview of what I want to talk today. So the first part would be the general introduction about why we want to consider encoding some quantum many-body systems. And then we would proceed to the concept of using neural quantum states and also simulating quantum systems using them. And the third part would be the mathematics, or I would say the mathematical structure of the neural quantum state ansatz. And the fourth part would be the frontier of the algorithm, meaning that what can we do beyond simulating ground states or excited states, and where we have achieved beyond time models of which only consists of quantum spin models in a chain interaction or something like that. And basically, the encoding part would be done up to this chapter 4, but if time permits, I would also talk a little bit about the real machine learning for quantum physics itself. Okay, so here I have shown 3 figures, which is not related with the one in the previous slide. So here, this would be the chapter 3, and chapter 4 consisting this red and blue boxes right here. Okay. And of course, you're welcome to pause at any time and ask questions. Okay, so let me start by a very general introduction. So when we say that we want to consider quantum many-body problems, what we mean is that we want to investigate the behavior of quantum mechanical particle that is interacting with each other in a very macroscopic way, usually. And this kind of problem is underlying many fields within, not only in physics, but also in chemistry and sometimes biology itself. For example, the field of condensed matter physics has considered the low temperature property of fermionic or bosonic degrees of freedom and have revealed many exotic phenomena such as a superfluidity or superconductivity or topological phase and so on. And as I mentioned, quantum many-body problems are also very important in context of chemistry, since it is going to dictate the chemical reaction at low temperatures, or sometimes it would give you the reaction rate, which is determined from the energy difference of some quantum mechanical levels, eigenstates of the Hamiltonian. And for example, this is related with artificial photosynthesis or material designs and so on. And also, it is involving the quantum information itself when we want to build quantum computers or quantum devices, quantum sensors, and so on. Also, it's underlying the statistical physics and through the concept of thermalization or arrow of time in the interplay of quantum and classical physics. And I would not go into details, but of course, we know that it is underlying high energy physics, such as the particle physics or atomic physics. And today's topic is mainly concerning condensed matter physics and also statistical physics, but the concept or idea of encoding quantum many-body problems itself can be also applied to other fields such as particle physics and atomic physics. And indeed, there are such progress toward that in research, which I'm not going to discuss in today's talk so much. Okay, so we know that there's methodologies to solve quantum many-body problems. And the first one is I would say is the most natural way that scientists have been thinking about it, which is the experimental investigation into the quantum many-body problems. So here we would consider observing, doing some real experiments on existing materials to find out what kind of natural phenomena is taking place in that material. And also another approach, which we know that it's going to work sometimes very well, better than the experimental, but sometimes not as well as the experiment itself, is to solve the Schrödinger equation in ab initio way by encoding all those atomic information into a single equation written down as here. And of course, in principle, we can solve this Hamiltonian or solve this equation and find out what is the eigenstate corresponding to each of them. And then find out what kind of dynamics would be realized or what kind of response we would get, or all those physical properties we can extract from that. But we know all nearly 100 years ago, Paul Dirac already pointed out that that kind of construction is not going to work out, since the continuous variable quantum many-body system itself is going to be too complicated to solve by itself. So what we have been thinking is to extract the essence of the quantum many-body physics and solve some modelized, I would not say toy model because some are very intricate itself, and solve the modelized to discuss the physics in that models, assuming that the model is going to capture the physics very well. So here I'm going to show the resolution of the quantum systems, with the right-hand side being the realistic, almost ab initio modeling, and the left-hand side being very abstract and hoping to extract the essence of the physics. So in the right-hand side, here I provide the first quantization of, for example, the electronic structure, but we can go down into the second quantization by using the notion of the basis which is usually considered in the context of quantum chemistry. So we can employ, encode all those information into discrete set of variables by representing some, by considering representative electronic structures, such as 1s wave or a 2s wave or such things that we discuss in hydrogen atoms, for example. And even more, we can extract and go into abstract side by considering lattice fermionic systems or a composite model that would involve both spins and bosons and so on. And we can also go on to extract, consider only two-level systems or only finite dimension systems in each levels. And also sometimes we can go on to extract more and more abstract models. But here is like overall view of how we consider the hierarchy of the quantum many-body calculation. And it is good that we can extract the essence from the quantum many-body systems, but still, even if we consider the quantum spins with macroscopic number of spins, that is still not solvable in the quantum using the most advanced classical computers or analytical techniques. And the underlying concept is the curse of dimension in quantum systems, which also happens in classical systems when we want to consider combinatorial problems and so on. But here I would focus on the version of the exponential increase in the Hilbert space of quantum many-body systems. So here, I would like to consider an electronic orbital of hydrogen-like atom as an example to see how it is going to show an exponential increase. For example, if we consider only the 1s orbital, then the quantum state, we assume that the quantum state would be spanned by four-dimensional vector, which corresponds to the fully occupied or one of them occupied or fully empty orbitals. So here we have two electronic spins, and each of them would have the degrees of freedom corresponding to filled or not filled. So the overall vector dimension is going to be 2 to the power of 2, leading to 4 dimensions. And if we allow the system to excite into the higher energy levels, including 2s and 2p orbitals, then we would have 5 orbitals in total with up and down spins, which would lead to 2 to 10 being 1,000 dimension vectors. And if we keep adding those higher energy orbitals, then we would see that the number of dimension required in the Hilbert space would explode like this. So only including the third one levels, we would have 9 digits over, which is around 1,000 over a million, I would say. Okay. Yeah, it's actually in the order of billion here. So obviously, it is not scalable to consider exact description that would involve all the dimension required to describe the system. And we need to consider some feature extraction of quantum states in order to tackle larger system, or at least in a system size that would allow us to extrapolate to the thermodynamic limit. Okay, in that, so we know that there have been a lot of works in that direction, including the work that would consider tensor networks or other condensed matter inspired or other field inspired variational states. But then I would like to introduce here is the new trend that is expected to overcome the limitation of the existing techniques. And that the bombshell or the start of that expectation is coming from this science paper published in 2017, which showed that one of the shallowest network structure is already powerful enough to encode the ground state property of strongly correlated quantum spin models, which I mean here the Heisenberg model with nearest neighbor interactions. So at this point, we didn't understand why it is working so well. And even now, we do not understand fully why it is working so well. But at least there has been some advancement in understanding that neural networks have the flexibility and optimizability and also the expressibility to encode the quantum many-body states. And here by flexibility, I mean that it is capable of reflecting the symmetry residing in the quantum many-body system. And optimizability, I mean that it is capable of using the abundant computational resource that is in usual sense in machine learning intended to be used under heavily parallelized context. So I would, in other words, these neural networks are now being developed very heavily under like TensorFlow or those machine learning oriented libraries, which is all very in good shape with the GPUs or the very hard many core computational resource. And I would say that this architecture is in very good connection with making full use of these existing computational resource. And another thing, which is not only limited to neural networks, but also common to other variational ansatz, is that they have the universal approximation theorem, which states that by adding more and more variational parameters or hidden neurons in the language of deep neural networks or restrict RBMs, we can encode arbitrary nonlinear functions at arbitrary precision. And of course, this statement itself is not very valid because we're not very happy to know that we need exponentially many variational parameters to reach some very small accuracy. But it is like the minimum requirement that we want for variational parameters, variational functions. Okay, so I would foresee the future of this neural network simulation, that it is going to provide us a new standard for quantum many-body simulations. Here, I mean, really the classical simulation, but not the quantum simulator itself. Okay, so here I have done the overview of today's talk, and now I would like to proceed to the concept of the neural network quantum states. And I don't see any question right now, but if there is at this point, please let me know. Okay, I don't know. I don't see the Slido by myself, so let me know if there is any question there. I would like to proceed to the chapter 2.
Up to now, there are no questions on slide, so you can continue.
Okay, thank you. All right. So in using neural quantum states, what kind of technique are required? So let me first introduce the concept of variational calculation. So in usual sense, or in the exact way, what we do is to write down the Hamiltonian. So we are going to allocate into some matrix what is the transition amplitude from one basis to another state, and then regard this as linear equation and solve this eigenvalue problem. And the good point, of course, is that there is going to be no error up to the machine precision and going to be used for small systems, while it is going to show exponential cost when we add more and more particles into the system. And instead, what we are going to consider here in the context of neuroquantum state is to introduce variational simulation to solve this eigenvalue problem. And of course, it is sometimes going to be hard to consider excited states, but when we want to tackle ground state, then we can use the variation principle that no other state is going to yield lower energy than the ground state. So we know that we can parameterize some state and optimize the parameters so the energy would be lower and lower. Someday, if the expressibility is enough in the variational ansatz, then we would reach the ground state. Or even if not, it is not capable of expressing in an exact way, still we can hope that it is going to capture the essence of the system. So in this sense, we are not saying that it is always going to reduce the cost. I mean, in the real way, solving the Hilbert-Hamiltonian of general local Hamiltonian is QM complete problem that we cannot address by classical computers or even quantum computers. We would hope that that argument is going to hold on large scale limit, but not in the intermediate scale where we can extract the physics in the thermodynamic limit. So this is the underlying hope for executing the variational simulation. So the caveat is that it is going to reduce the effective dimension of Hilbert space, but it is not assured that we are not going to reach the exact ground state. Okay. So variational simulation is in very short way, we can express that we are solving some equation instead of the exact Hilbert space within the parameter space, such that the solution in the full Hilbert space is approximated. And the key steps, I would like to raise 2 points as key steps for doing this. And the first one is to choose appropriate variational principle. And for example, in the context of neuroquantum states, this is going to be the metric between states that is under exact imaginary time dynamics and the actual variational dynamics. So I skipped very much here, but when you want to simulate, for example, the ground state of the quantum many-body physics, what we would usually do, and what people usually think is very efficient, is to perform the imaginary time evolution that is presented as operator here. So by increasing the imaginary time tau here, we would expect that the higher the excited state amplitude within this ansatz is going to be suppressed more and more, hopefully in exponential order. And at some point, we are going to reach that exact ground state. But we know that this operator itself is going to increase, is going to have exponential cost. And we want to replace this with dynamics within the variation parameters right here. So the question is, what kind of delta theta would allow us to approximate this exact dynamics as much as possible? So this is going to affect the simulation accuracy and also the efficiency of the algorithm very much. And the second very important point is is the choice of the ground state approximant, or which we call variational ansatz. And here we have introduced theta. I think I forgot to mention this, So when I have theta here, I mean that the psi is represented not by the exponential length vectors, but instead set of variation parameters. And people in condensed matter physics have done this very well for specific tasks. For example, the resonating valence bond state for spin liquid has been very successful, not for the cuprates, but for other kind of strongly correlated materials. And also the Laughlin has also proposed the Laughlin state to explain the fractional quantum Hall effect. And these attempts has been very, very much successful, but we would say that we need a very deep physical knowledge into each physical phenomena, which I don't think is a very scalable way to advance in the future. So in another way to say this, requiring the deep physical knowledge means that we are going to perform some bias search into the state. So at some point, we're not sure, but it may not be necessarily suited for searching to account for unknown phenomena. In this context, we would say that we need physics agnostic variational function that would allow us to explore the unknown phenomena in unbiased way.
Okay. Sorry to interrupt. Yoshioka-san,
Yeah.
There is a question in Zoom chat.
Yes, thank you. Will you share with us
question.
an example of psi theta? Yes.
Yes, it is my question because I didn't understand that psi theta. What is theta? It's their variational parameters. How do I know which parameters to use? So can you give us an example so that we can, it's clearer? Thank you.
Yes, of course. So yeah, maybe I would come back later. Yeah, of course.
Okay.
Wait. Yeah. So for example, I think this is very clear to show. I would first introduce this state. So here, for example, variational parameters theta would be the network. In the context of neural network, it would be the parameter itself that resides within that neural network.
So wait.
Or more I think it's more straightforward, for example, to consider the case in regression, for example. When we want to do some linear regression to account for some data, what we do is to optimize the slope and also the height where we have the line. And so we would have two variational parameters to account for some given data. So it is like the degrees of freedom to approximate the data you have in your hand. So for polynomial functions, it is going to be the coefficient for every powers, for example. Okay. And if you have exponential function, then you would have the exponential. So let's say you would have exponential to minus cx or something. And then in that case, coefficient c is going to be the variation parameter.
So in this case, I have some Hamiltonian and I have some initial state, right? And
yeah,
in this, and I want to find the ground state of the Hamiltonian and stuff. So in this case, what will be my parameters?
So you mean the initial parameters or the parameters? Okay, initial parameters, it can be anything in principle. So as long as the initial state has finite or more than exponentially small overlap with the actual ground state, then the imaginary time evolution is going to assure you that at by increasing tau, you would reach the exact ground state. So you need to be careful that some given theta 0 at initial state is not like completely orthogonal to the ground state, but that is in many cases doable. For example, by considering some mean field solution or something like that. So in that case, what you would do first is to compute the mean field solution, and then think what kind of variational parameters are going to realize that mean field solution, and then run imaginary time evolution.
Okay. Right.
Okay, I hope, yeah. So if it is not clear, yeah, variational parameter is like any kind of nonlinear function. Variational ansatz can be any kind of nonlinear functions that such that, for example, you can normalize afterwards the calculation, for example. And here I consider very generic form of variational ansatz. And theta is like, here I'm introducing as abstract way of representing the tunable parameters in the function.
So sorry, my original question was, it is like very abstract. Could you share with me a concrete example? That was the question. So it's clear because I don't understand it in a clearly.
Yeah, so maybe
Maybe we can do it later. Thank you.
yeah, I
I've taken
think
so much
it
time.
would be clear when we reach the neural network example.
Thank you.
Yeah, thanks for the question. Okay, so yeah, the variational parameter theta is going to be abstract for a couple of slides. So, but let me say that it is simply parameterizing the nonlinear function. And the idea of neural quantum state is the following. We consider the wave function as a mapping from some computational basis into the amplitude of corresponding to that basis. So for example, in the case of the hydrogen atom, which I introduced here, we would like to represent these coefficients C1 to C4 by some simple or nonlinear function. That can be polynomial function, or it could be exponential, or a combination of exponential, or so on. What you want to do in the neural network state is that we would have some function that would take whether the electron is occupied or not, and returns you this C4, or the coefficients for the computational basis. So that is the general concept of the neural network. So I think it is for if we want to do this in an exact way, then as I have mentioned, we can solve the linear equation and get the exponentially long set of vector, and then the amplitude would be each entry of this vector. But what we want to do here is approximate each entry by some nonlinear function. So this is the case for the wave function, where we can have, which is straightforwardly expressed in terms of vector, but we can also generalize this to express density matrix as well. So since it is a density matrix, here we would have this nonlinear function would take both the x and x prime, so it's in the row and column, as an input, and returns the complex amplitude corresponding to this x and x prime. And in principle, we can consider any types of nonlinear function to do this task, but the idea is that we are going to use a neural network that would take these computational basis values and output the amplitude corresponding to them. Okay. And I think it is instructive to introduce the details of what neural networks are when we want to understand which part is corresponding to the variational parameters. To do that, we would start by considering the perceptron, which is like a single layer, single hidden neuron, the most simplest neural network. We can consider this as generalized linear regression in a sense that what this unit does is to take the array of input vector xi and add them up and do some linear transformation like this. So here we would say these, so for example, input x1 is going to be weighted by w1, input x2 is going to be weighted by w2, and so on. Here, this weight w is going to characterize the behavior of the nonlinear of this function, as you know. And of course, we're not going to finish only by this weighting w, but afterwards, we're going to introduce some nonlinear activation functions. And yes, I haven't provided a concrete example, but this nonlinear function can be any type of things in principle. And for example, in the very first proposal, a function called sigmoidal functions was used, or for example, hyperbolic tangent or functions were used in the first stage. But now they have proceeded and found out that it is more, we can get more high accuracy by considering a function that would show zero output up to some threshold, and then return linear weights for the input. Yeah, so that is in context of machine learning, and the optimal choice of nonlinear activation would rely on what kind of problems we consider. But here, in context of neuroquantum states, they're not like special way of investment in this direction, and we are simply using the state-of-art type of functions considered in deep learning. Okay, so now we have understood that each these circles are going to execute some linear transformation and then nonlinear function. We can stack. Yeah.
Why do we have to actually add the nonlinear element in here? Is that just something that we have tried and tested, or is there like a reason for it that we understand?
Yeah, so the reason we introduce nonlinear ones is first, it is going to allow you to express more flexible functions. And second, which is the most important, if we don't have any nonlinear function, then everything is going to be linear. So there's no point of considering multi-layer functions. So without the nonlinear function, everything is going to be linear regression. And the expressibility of linear transformation is quite limited. So that's why, that's the main reason.
Okay, thank you.
Yeah, thank you for the question. It's very helpful. So once we have one single perceptron, we can stack these units to form deeper ones or wide neural networks. I'm not going to details of like what is the trade-off between making wide or making it deep, but you can understand that simply as more units you have, the expressibility is going to be enhanced. So as I have shortly mentioned, we would have this by stacking more and more units. This function is going to be a universal approximator of nonlinear functions. And in principle, we would all these lines connecting the circles are going to represent the linear weighting parameter, and which is followed by nonlinear functions here. So what this multi-layer perceptron does is to first consider some linear transformation, do some nonlinear function, and then nonlinear transformation, nonlinear one, and so on. Okay, so as much as these lines, we would have many parameters within the neural networks. And these kind of nonlinear functions has been used mainly in two directions. First, as a discriminative model, and the second to be the generative model. So what I mean by discriminative is that I think it is more intuition straightforward to look at this example. What it does is, for example, the image recognition, meaning that it would give in some data, and that output from the network is a label corresponding to this input. For example, maybe this neural network is trained to output what is the probability of the input image being cat, denoting the cat or dog or a lion or so on. And also neural networks can be used as a generative model, meaning that here the neural network is not going to give you some label, but it is going to approximate some given probability distribution. And one of the most prominent example of using deep neural networks for this purpose is the example of the AlphaFold, which takes the sequence or information about DNA configurations and output what kind of the protein structure could be expected from that. Okay, so in this problem of the AlphaFold, it is known to be a very super hard problem that was to be, I wouldn't say it is solved at the current point as well, but it made a major advancement because it has provided a way to do a search dimension over 10 to 300 dimensions. So, for example, what I like very much about this AlphaFold is that they made it open source so that everyone can test using those GitHub codes. And I saw in Twitter that one professor in Todai was like suffering for some protein structure for years, and then just tested on this using this AlphaFold to recognize what was the actual structure. So yeah, what I wanted to say here is that strong representability of neural networks are going to benefit us in context of, we hope that it's going to benefit us in context of quantum physics as well. Okay, so I have introduced two ways of thinking about the neural networks. And so one way of using them was the discriminative modeling, which is represented by image recognition. And people have first started using, considering to use neural networks in a similar way. For example, instead of outputting the labels corresponding to the objects in the image, they considered, including me, putting in some physical observables and output the corresponding phases as labels. And so the section 6, chapter 5 is going to be this kind of research direction, but I'm afraid that I'm not going to have enough time to proceed that, I guess. And the topic today I'm going to talk about is rather in line with a generative modeling, which aims to encode the complex probability distribution of the wave functions or quantum states. Okay, so I hope this is going to help you in analogy of how we are using neural networks in the context of quantum many-body states. Okay, so since I have provided more concept about using neural quantum states, now let me proceed to the actual what is a neural network considered and what is the parameters and what we can get from running the simulations. So I have explained that the main idea is to consider that the coefficient of each computational basis as a function from spin configuration to some amplitude. And what we consider here is to use what was considered in the paper of Carl Leo and Troyer was to use Boltzmann machines to represent this nonlinear function. So what I mean here is that this amplitude is approximated by this function here, which can be seen as a complex interacting Ising model. So here, each sigma is representing the physical spin degrees of freedom, which is interacting with another auxiliary introduced hidden spins, which takes binary values ±1. So we would consider that the amplitude of this computational basis sigma is going to be given by this value here. Okay, and why we call restricted Boltzmann machine. So one reason is that this is like exactly the Boltzmann distribution corresponding to the basis sigma, and with two body interactions. And why we say restricted is because the interaction is included only between red and blue circles, denoting the physical spins and hidden spins right here, but not between hidden spins or between physical spins right here. And the reason they didn't introduce interaction between these is simply because of computational reason. I would later go on and show that tracing out this auxiliary degrees of freedom H can be done analytically if we don't have any interactions between these blue and red circles. Some common properties of these neuroquantum states is that, sorry, I have a typo here. Physical observables would be evaluated via Monte Carlo sampling. And in many cases, we're not going to execute the exact tracing out of sigmas, only for debugging or something like that. In the when we use RBMs, for example, what we can do is efficient computation of unnormalized amplitudes. So this means that we can perform, for example, Metropolis Monte Carlo technique to sample from psi squared like this. And once we have access to the psi squared and sample arrays, lots of spin configurations, we can estimate the observable O by considering a property named that local energy, like here. So in principle, any kind of physical observables are going to have some non-diagonal terms, but using the ability of the neural network ansatz to compute the unnormalized amplitude, this is going to allow us to compute the ratio between different computational bases in in polynomial time. And with this, we can compute this, the sum over this expression. So for this entry, O tilde, we can perform the Monte Carlo sampling and compute each diagonal elements, which would allow you to compute, sample the physical observables. Okay. And I have already mentioned the universal approximation theorem, so I'm not going to go into details. Yeah, I just wanted to say that similar to other types of deep neural networks, this the shallowest type of neural network would also support that kind of argument as well. Okay, so once we have introduced the variational ansatz, what we would do is to optimize the theta or the network parameters, the WAB, such that the energy expectation from that state is going to be minimized. This can be done in various ways, for example, by the simple gradient descent, by computing the gradient with respect to each parameters, or we can also perform higher order optimization technique, which is, and so this natural gradient or the stochastic reconfiguration is going to perform something like Newton method and going to assure you to converge to the ground state in faster way than the usual gradient descent. Okay. So since this is going to require you to compute each entry of the quantum information matrix for the variation parameters, this means that we need that being the n of variations, we need n times n entries of this information matrix, and also compute the inverse matrix. So the computational cost compared to the usual gradient descent would be much, much higher. But in practical way, we use this technique since it is, after all, faster than just doing the gradient descent. And also that this is sometimes going to be stuck in local minima. Example of running this kind of natural gradient is shown here for a one-dimensional antiferromagnetic Heisenberg model with lengths of 22 qubits. So for example, if we use the raw RBM variational function, we can see that the number of Monte Carlo sampling is too few, so we're not going to reach that exact state. And this is can be remedied in many ways. The trick considered in this figure is to introduce some physical constraint into the expressibility of the variational ansatz, only to capture the translationally symmetric space of the Hilbert space. Meaning, so this model has the translational symmetry, so each eigenvector is separating within each symmetry sector. So here they use a trick to kick out those symmetry not preserving sectors. So this is going to allow you to reduce both the sampling error and the systematic error in the optimization. Okay, so in the paper of Carleo and Troyer, they considered much larger system with much larger Monte Carlo sampling and tackled three models, in being that transverse field Ising model in 1D, antiferromagnetic Heisenberg model with 80 spins, and also two-dimensional ones. And the most remarkable one is this two-dimensional example, which they showed that they can surpass the performance of tensor network states simulated on periodic boundary condition. So the caveat here is that these tensor network methods are mainly to be executed under open boundary conditions. So it is not like their best practice actually, but still it was remarkable to the community that we can achieve the state of the art using the neural network ansatz. So here, the parameter alpha is denoting the number of the variational parameter, or more precisely, the number of the hidden spins considered in the model versus the physical spin you would have. So it is very evident in the case of one-dimensional case that by adding more and more variational parameters, you would see exponential suppression of the accuracy compared to the path integral quantum Monte Carlo. So this paper of Carolina and Troyer was considering a model and benchmark test for a model that can be solved using the quantum Monte Carlo, meaning that there is no time problem at all. But still, it was very exciting for the community, and including me, people have considered applying and also making it more powerful to tackle the frontier of the quantum many-body states. And here I would like to introduce three main directions for that, which I showed in the agenda thing. First one is the algorithmic development, how we can go beyond ground states or real-time evolution and, for example, tackle finite temperature problems or open quantum systems or doing some inverse problems or so on. And the second one is the mathematical understanding of the ansatz. We know that deep neural networks are, or even the shallow neural networks are very powerful, but why does it work? That is not completely answered at the current stage. And I believe that it will be very hard to completely answer that problem. It will be a long-standing problem. But I would like to introduce some advancements that has already been made in the community. And together with the algorithmic development, I would also like to introduce a practical application that is done in context of investigating quantum spin liquid systems or so on. Okay, so
there is a question from Slido, and we pasted the question on Zoom chat. So
okay,
please, yeah.
So what is the computational complexity in ground state simulation by RBN computations? So this is a very good question, and this involves a lot of like layer resolution that I can say. So in the real, to be very honest, any kind of variational simulation is going to be exponential cost in complexity way. But I think the questionee wants to ask what is the computational cost for each step, I guess. So for that, let me get back to the previous slide. Okay, and I think it is these two equations are going to answer your question, because the computational complexity is going to be determined from by this product of the cost per iteration and the number of iteration. Or in other words, the overall cost would be how long it took for one iteration and how many iterations you would need. And so I can break up this question into two parts. So for how long, how many iterations we need, we don't have concrete answer for that. We don't have mathematical agreement for that. And how long it takes for simple iteration, we know from these equations. When we use a gradient descent, it is going to be order n, with n being the number of parameters, because simply we are going to compute the expectation, energy expectation. And also, actually, it involves the number of sampling, but in large system size, it is going to be dominated by this gradient simulation. And in the case of natural gradient, as I have mentioned, it is going to be n cubed, with n being the number of variation parameters. So I hope this is going to answer your question. Yeah, so I think I would like to, it is good time to take a break here. And maybe if there's any other questions, then I think we can also take that question as well. Shall we take like a 10-minute break here?
So, yeah, sure. So we'll have a, we'll start again from 2 to 12, okay, at PM. So,
okay, good.
Yeah. So, for, yeah.
Okay,
thank
yeah.
you, Yoshikawa-san. Yeah. So So it's time to resume the lecture. So Yoshioka-san, if you are ready, could you please start?
Yes. Okay. Yeah, so let me proceed and resume from the chapter 3, which is about the mathematics about the neural quantum states. So here I'm going to talk about the relationship with other ansatz, which would mainly be the tensor network, and also how to encode actual states that whose exact description you already know. And also I would talk a little bit about quantum correlation in neural networks, which I would mean by that entanglement entropy in pure states. Okay, so here is the overview of what people have done, including me, about the mathematics of the neural networks, quantum states. Here, what's been done is summarized in these 2 words. So we have been thinking about constructing exact description or transformation of some state into RBMs, or RBM into another ansatz or something like that. And also we have considered the property of random neural quantum states. And I think why people have done this is the reason is that we want some figure of merit for the variational ansatz, meaning that given some state, we would like to know or understand what is the physics encoded in the variational ansatz, or how well we can describe the quantum state. So there was a question in the previous session the previous chapter, what is the computational complexity of simulating some ground state? And the best thing the best is that we can exactly know what is the computational complexity given the state, but that would be done when we know what is the figure of merit. So this would be the bond dimension versus the entanglement entropy in the context of the tensor networks. But actually elucidating this kind of figure of merit would indeed become a major breakthrough that would include also the deep learning community. But this has not been done in theoretically yet, and I envision that this is a very difficult problem that we need to build up one by one. So here in today's talk, what I would like to focus on is what has already been done and what could be possibly done next. Okay. So what has already been done in mathematics is to, as I have explained, it is twofold mainly, and it involves exact expression and also the quantum entanglement in neural quantum state. For the first, I would first talk about the exact expression by RBM, and I hope this is going to provide you better understanding on that itself. And then proceed to the relation with the other ansatz, including tensor network and condensed matter inspired ansatz. There is some work that investigates that relationship with variational quantum circuits, but I'm not going to get into details considering this direction today. Okay, so getting back to that to the expression by RBM, since it is analytically very straightforward to understand, we have seen already introduced the expression in this form, which is denoted by the Ising-Wise interaction between the physical and the spin neurons. And as I have denoted, since there's no interaction between red and blue circles, we can trace out this H hidden spins and write down the expression or amplitude of some computational basis in this form. Okay, and we would like to wonder what kind of states we can express by this this ansatz. One of the most simplest one is the trivial case of the plus state, meaning superposition of spin up and spin down. Here I'm going to denote spin up and down interchangeably with plus minus 1, since I guess it is quite natural in that way. So with a bare neuron, which does not have, it is not exposed to any magnetic field at all, then we can straightforwardly compute that the amplitude becomes this expression, which would be superposition of spin up and spin down like this. So I guess this is very straightforward. And next proceed to 2-qubit case as a warm-up. And so how can we construct the network parameter for this case? The answer is we can simply add one hidden spin and keep the magnetic fields to be 0, but introduce interaction amplitude as a complex value like this, pi/4 times the imaginary unit. So plugging these parameters into the expression of hyperbolic cosines, we would obtain this cosh of these ones. And since hyperbolic cosines with imaginary values would become the usual cosine function, we would arrive at this expression. So this would tell us that the amplitude is completely 0 if sigma 1 and sigma 2 is plus, yeah, sorry, this should be flipped actually, and sorry, this should be minus imaginary, and all these values should be minus I here, yeah, to represent the spin up down minus down up. Yeah, this is my bad. Okay. But in a similar way, we can set all the parameters to be something like in this form and show that quantum states using quantum information such as the GHZ or W states can be represented by RBM with order linear and hidden spins as well, where GHZ means superposition of, it's like cat state of 0, 0, 0 and 1, 1, and W state meaning that among n qubits, only one of them is plus up spin, and other ones are all down spins. And we would have superposition of n states like that. That is the W state. Okay, so since now we know how to construct the Bell state for 2 qubits, we can combine or simply have a bunch of them and line them up in this form. So for example, if we have 6-qubit case, we can couple this spin number 1 and 4, 2 and 5, 3 and 6 to yield a quantum state that is entangled, maximally entangled when we consider the bipartite by cutting in this halves. So in other words, by tracing out the subsystem in the right-hand side, what we would have is a maximally mixed state as a reduced density matrix. So any kind of Renyi entropy with arbitrary alpha would be this value, and over 2 with times log 2, which means for any alpha, we can achieve the maximal value of the entropy. So we can show that maximal entangled state can be represented in very efficient way using the RBMs. Okay, and so that was for the maximal entangled case. And before proceeding to the volumal entangled state, let me go on further into the combination between quantum information a little bit. So when we look at this term, we notice that we would have the product over this hyperbolic cosine, which means that each hidden spin would perform as non-unitary operators onto each of entry of the Hilbert spin of the quantum state vector. And when I say this non-unitary transformation, it is not like the most general ones, but since as we can see here, it only involves sigma as an expression. So it would have diagonal non-unitary transformation. In other ways, we can consider that each hidden spins would have non-unitary weighing into the entry of the state vectors. So I would later explain what stabilizer states are, but we find that this kind of construction is, or the previous works have found that this is in very good connection with constructing stabilizer states. Okay, so what expressing stabilizer states in neural network itself would be like, okay, that is very fun and good, but the next possible direction is that we can use all those exact representation to investigate the effect of noise into the quantum system. So it's not only like toy model make us happy thing, but it could also be beneficial in terms of quantum computing or quantum simulations. Okay, so what is stabilizers anyway? And I would take the toric code state as representative, most famous stabilizer state for the condensed matter people. But let me first provide the general definition about this. But first, I would like to define the poly group, which is composed of the tensor product of all possible poly operators. So let's say we have an n-qubit system, then the poly group is composed of the tensor product of all those operators with global phase up to exponential pi over 2. Okay, and from stabilizer group is defined as subgroup of this poly group, in which is whose element is commuting with each other. So, for example, in the 2-qubit case, poly group would all consist of I times x, I times poly y, and all those terms. But the stabilizer group, one of the stabilizer group would look like this. So here we see that all x and y's are going to anti-commute. So if you have 2 of them, then all these terms are going to commute with each other's. Instead of 4 terms, you can also consider two terms like this and see that this also consists a group, since you can anytime produce the identity term by considering the product with itself. And when we say generate stabilizer generators, we would take the maximal set of individual elements in this group. So in the example of 2-qubit stabilizer group with 4 elements, then generators would be only XX and ZZ. And here we impose that all elements should be individual. We would not include I and Y's, since we can produce this by operating into one another. Okay, so since we know what stabilizer generators are, now we are ready to introduce the stabilizer states. So stabilizer states means that a quantum state, which is +1 eigenstate of all the eigen stabilizer generators like this. So in the case of 2-qubit stabilizers, this is Bell state is going to be the stabilizer state of this kind of generators. So here I I flip the sign so that it is in good connection with the Bell state I already introduced. Okay. And for the case of 3-qubit generators, this can be something like this, which would stabilize the GHZ state, which I introduced in the previous slide in oral way, but not in the in equations. So n-qubit GHZ is going to be a bunch of zeros, n bit string of zeros, and also superposition with n ones. With, however, the generators are going to be much more complicated. So I'm not going to show here. Okay, so at first it seems that this kind of stabilizer states are going to be hard to encode, but since we know that all those generators are commuting with each other, we know that we can prepare some superposition state and do projection onto the +1 eigenstate like this. So observe that this 1 plus s is a projection operator, since all we are considering a Pauli product. So it's all, if you consider the squared term, it is always going to be identity, which means that the eigenvalue is ±1 for all of the stabilizers considered here, which means that we are going to project out the -1 eigenstate by considering this type of summation. And if we consider projection for each stabilizer generators, then we should end up having this stabilizer state defined here. Okay. So naive strategy is to encode all these terms into the neural networks, such that the operations would be represented by networks. And it is very naive, and at first sight does seem to work, but of course I'm not going to show here, but we can find out that that strategy is not going to work for generic stabilizer state. And there's no proof, but at least when stabilizer consists of only X and Z Paulis, then it seems that this kind of construction is going to work to produce RBM expression of stabilizer states. Okay, so let me proceed to introduce the Kitaev surface code state and also the corresponding stabilizer states. So as I think condensed matter people, some condensed matter people are familiar with this concept, but here the stabilizers are all possible product of Pauli Z operators in this phase-wise product, meaning that when we consider 4 vertex for the face of the 2-dimensional array here, we call this a face of the array, and we call it a face operator when we build up a product over sigma z for this face. And in similar way, we can also introduce a vertex operators that here, which we now focus on the vertex of this 2-dimensional square lattice. When we consider now Pauli X operators, product of X operators on the 4 sides of these operators, then we call them the vertex operators. Yeah, so, and it's a little bit embarrassing because here the definition is opposite for X and Z, but we can simply switch them interchangeably. Okay, so we can show easily that all these A terms, A operators and B operators, are commuting with each other and going to compose a stabilizer group of this system. And the Kitaev toric code state is obtained as this form, meaning that we would project all the -1 eigenstates of this corresponding to this stabilizers. So And we can find, or the quantum computing community have already found, that this type of operation can be done by adding some ancilla in between these square lattice and do a controlled A or controlled B operation and then trace out the ancilla again. So this can be more understood using this figure, I guess. So here, this two-dimensional array is now tilted, and we are having the three-dimensional vision for the states. So here, for the face states, I hope it is not flipped, but what we do is to prepare each qubits on these edges into plus state, and also prepare some ancilla into plus state as well, and operate some control Z with each of them, and then project out this ancilla into plus state. We do this for the vertex sites, but with the difference that it is we're having the C naughts instead of the CZ gates for here. So this is how they do using the actual gate operations, but we the paper of Dongling Den and others have found that each of these steps can be translated into the language of RBM. And they found that for each of the space and vertices, you can prepare hidden spins coupled by amplitude of I over pi, I pi over 4 or I pi over 2, and reproduce the stabilizer state. And so in this page, we don't have the reference, but in their paper, they also show that all the stabilizer state with sometimes -1 eigenvalues can also be represented using this structure of RBM as well. So this itself is like finding some funny relationship between neural quantum states and quantum information, but this could have some practical usage in simulating the effect of noise of surface code fault-tolerant quantum computing. Yeah, and there are some follow-up works that consider other types of topological orders as well. And in the paper of the proposal for a 2D toric code, they already mentioned that this is possible for 3D, but there are also some follow-up works that the quantum codes that is starting from the graph states, which means that we first prepare a plus state and do some control Z operations, that kind of quantum codes can be represented by using neural networks. Sometimes introducing hidden spins with plus, -1, +1, and also 0 state. Or in other words, hidden neural networks that uses hidden spin with ternary degrees of freedom. Okay, so that was the connection between the quantum information. And next, let me proceed to the mathematical understanding of the neural quantum states by further looking into relationship with other variational ansatz. And here we would consider the tensor network as the primary example, since it is heavily used in context of quantum many bodies calculations. So here, for example, tensor network, for example, here I intended to mention the matrix product state as the primary example. So that kind of tensor network construction would mainly focus on quantum states with small entanglement entropy, which is defined as the von Neumann entropy of the subsystem when you trace out the remainder of the system. The MPS is written I think many of you have ever seen this picture, but is graphically represented in this form, which actually means that the I need summation over sigma here, but whose amplitude is represented as the matrix product of these in this form. So the characteristic of the MPS is that when you consider a matrix of size d by d, then the total system entanglement entropy would always be bounded by log 2d. And this straightforwardly implies that this ansatz is capable of representing a quantum state with area law entanglement, and which is satisfied in 1D gapped ground states. So simulation of 1D gapped state is now believed, or I can say that it is proven to be efficiently done using the MPS states. So so here the paper of the Oros was showing that there is a hierarchical structure in the many-body Hilbert space, which is which we can understand in terms of small or big in quantum entanglement in the system. So as I have mentioned before, it would be very nice if we have this kind of quantity, bond dimension and entanglement entropy, also for the neural network states. But I guess that is like a very important and difficult question. Okay, so the relationship between RBM, neural quantum state, and MPS has been already been studied by paper of Chen and others. And they found that there is a relationship between two that would map into each other exactly. But for example, this transformation is not very practical in a sense that if you want to transform RBM into a tensor network or the MPS, you need exponentially many bond dimension in general. I think this is quite natural with the picture, this network picture, because you would you can see that there would be some entanglement between if you couple two sites by hidden spins. And that it is the other way around is also true in a sense that if you want to transform MPS into neural networks, then you have to solve a nonlinear equation that would not have solution in general. And let's say you have for each hidden spins, you have to solve variable n equations, then that is not going to be practically useful in the context. So it seems that MPS and RBMs are not in a very good shape, but other works have found out that if you change of view and look at other classes of neural networks, it is indeed a very good connection. So here they considered a type of neural network named the recurrent neural network, and which have a class, which is a class of neural network defined by conditional property, meaning that they would use the transformation that any kind of amplitude can be rewritten in this form. And what the original paper of using RNN for neural networks is that they would parameterize these conditional properties P using the networks. Okay, so here this is graphically presented in this form. So here what they found is that from MPS, they can obtain this specialized type of RNNs in which they cannot do the DMRG anymore, but still can do VMC type of optimization. it was surprising they found pointed out in like a paper of 10 years ago that any RNNs of like special structure can be essentially be written by MPS. So and this was a paper of like deep learning community and not completely unrelated with quantum physics, but it's quite interesting finding. Okay, so using this kind of network structure, they can use MPS as starting point of the simulation. For example, you can consider using DMRG at some point and then switch to this RNN type and allow some additional operations. And then you can find that this ansatz allows you to explore even more complicated structure of quantum many-body states. So in this paper, they executed a simulation of Heisenberg model on square lattice and also the triangular lattice of 10 by 10, and found that in terms of variation parameters, this kind of generalized RNN structure is going to allow you to efficiently reach the ground state. And considering the relationship with other ansatz, you can ask, are deep neural network even more powerful than the shallow ones? And we know that this is true in the context of deep neural network, but it has been also theoretically shown by these people that there are some classes of quantum states that deep Boltzmann machines or deep feed-forward neural networks are better at capturing. For example, in the paper of Shagir, Sashwat, and Carleo, they showed that the fully connected neural network would allow you to express the class of this fully connected neural network would involve both MPS and PEPS, which is like two-dimensional generalization of MPS, that can be contracted with polynomial cost. So as a caveat, I would like to mention that PEPS in general is not contractable by polynomial cost. So there is a strong constraint in this figure here, but still it is very interesting to see that this kind of relationship holds. Okay. So that was the relationship with other tensor network. And now let me proceed to describe the quantum entanglement captured in random neuroquantum states. So in the work of Deng in this PRX paper, and also the recent paper by of this Sun and others, they considered what is the entanglement entropy realized in randomly parameterized neuroquantum state. So here, y-axis denotes the von Neumann entropy, the half-chain von Neumann entropy, divided by the system's size times the log 2. So when you reach the value of 0.5, then that would mean you're saturating the half-chain bipartite entropy. So this lambda is the number of the hidden spins. So you can see that by adding more and more parameters, you can reach more and more entanglement regime. So, and it seems to approach nearly saturating value of maximum of the page value around here when that ratio is set it right like this. We have already seen that the maximal entangled state, which correspond to the top of this pyramid, can be exactly represented by RBM state, but also by setting the parameters randomly, you can also reach the usual volume law entanglement entropy as well. But what they found in the paper of Sun and others is that although they seem to capture the randomness very well, they don't possess the random design property. So it is not going to allow you to efficiently simulate quantum randomness or so on. And another interesting thing is that by adding even more and more hidden spins, the entanglement entropy seemed to show some destructive interference with each other. And at some point, you are going to this curve is going to reach zero at even at the top of this mountain. Right. And there has also been some investigation about the number of parameters required to satisfy volume law. And of course, we know that tensor networks are not very good at doing this. So we know we need exponentially many variation parameters to do this. On the other hand, as we have seen in the RBM case already, we need order n variation parameters in the case of RBM, and n squared in case of the fully connected case. Whereas this is for the 2D case, the convolutional neural network seems to be the most efficient among these three, since it uses utilizes the translational symmetry, meaning that it would here we would consider a network that is whose one gray perceptron is connected to a finite number of neurons in the input, with the network's parameters all translated into the next or all among all the layers around here. Okay, but still, it is. And we can see the striking difference between the neural networks and the tensor networks in terms of capturing the volume law. So, although this would kind of highlights the difference between the different variational states, we are still not at the point of fully understanding what is the figure of merit for the neural quantum state. So in that direction, we would like to proceed more, I guess. Okay, so I have talked about the mathematics of the ansatz, and next I would like to proceed to the what we have done using the neural quantum states. And that would involve simulation of finite temperature states, or what we have done beyond the time models already. And I guess it's a little bit early, but it's good timing to take a break here. So
yeah, okay. So for audience, if you have any questions for Dr. Yoshioka, maybe it's good time to ask questions. So may I ask a question?
yes.
So in tensor network simulation, the advantage of the tensor network, in case of the simulation of the quantum circuit, is shallow circuit and many qubits. So on the other hand, for using machine learning techniques, is there any research to simulate quantum circuit, such as So this is my question.
I know. Yeah, thanks. Yes. Yeah, I know that there is a work by Carleo that mapped QAOA kind of variational circuit into neural network, so that we can simulate with lower computational cost.
I see.
But on the other hand, for the general so QAOA is like the combinatorial problems, which consists of only ZZ interactions with each other. So we can see, so if there's only ZZ interactions, then the rotational Z is going to be diagonal. So we can understand that it's in good shape with neural networks. But for the usual, for general quantum circuits, it is not very much because, as I have explained, so since neural networks are rather performing non-unitary transformations in diagonal way, yeah, I think for the general quantum circuits, it's better to use matrix product states or tensor networks. Yeah, and I guess it depends on the situation.
I see. For example, in simulating the quantum circuits such as quantum Fourier transformation, can we express this circuit by using RBM state? Could you guess?
For the QFT, yeah, if the state is already given as, So the point is that actually we can always rewrite quantum circuit using neural networks, but not a neural network that we can simulate classically efficiently. So that's the point. Yeah, so in that sense, if we are given some QFT circuit and given some input quantum state as neural network, then we can map this structure into deep Boltzmann machines. But the network parameters would be complex valued. So we would need some trick to simulate this complex valued neural network states. And we, so as I have introduced, this is possible for shallow neural networks, even if it is like complex valued, we can still compute the amplitude since it is shallow. So meaning that we can compute the partition functions, not the partition functions, but the amplitude efficiently. But for the case of deep neural network, deep Boltzmann machine, this would be harder. So yeah, I think it is possible if you have input as neural network.
Yeah, thank you. So okay, is there any other questions? Okay, so let's have a rest.
I've got a question. Is that?
Yeah,
sure.
Could you actually explain? The slide number was 34, I think. So it was. Yeah, QTFs. Yeah, I didn't understand what are the vertices and faces here, because you know, this torus does not have a vertex and a face. So what is this actually? It flew over my head. Could you explain it again?
Yeah, so face is, what I mean by face is this the square, 1 unit of square right here, denoted by the red circle here. So a face, in a more precise sense, face means a set of 4 sites that would consist this diagonal here around, which is surrounded by the circuit. And when we say vertex, so vertex, it's like a jargon for the surface code people, but we would like to denote a set of 4 sites surrounded by this green circle here. So when we say vertex operators, that this means that it's a product over 4 sites over here, and face operators are like the product of operators over 4 sites in this faces.
Why is there a donut here?
Oh, sorry, you were slightly disconnected.
Why is there a donut here? And what's this? What does this have to do with this donut that we are actually showing here?
So the donut is like intended to show the total system, which is periodic in both x and y axis. So if you consider a square lattice with periodic boundary condition in both directions, then you would have donut kind of structure.
Okay, so we're taking a patch from the surface of the donut and we're showing it like that. So, okay.
Right. So we are taking this batch surrounded by black curves here and showing where the qubits are residing. Right.
So what does this topology actually accomplishes?
So this topology would allow you to have it is going to be related with the degeneracy of the stabilizer state. So we can also consider topology with 2 donuts that is connected to each other, which would give you 2 circles in the center. And this number of centers or the number of holes are going to give you the degeneracy of the stabilizer state. In this case, we have only 1, so the degeneracy would be 2 to power 1, and there would be 2 stabilizer states, in fact. But here I'm like kind of giving one type of construction.
Could you actually summarize? There was a summary yeah, this 43. Could you go to the book?
Maybe we can like go into the break session first and
yeah, sure. I'm sorry.
Yeah.
I'm sorry.
So right.
Yeah.
Maybe we can take like another 5 minutes for
Okay,
something.
sure. So we will restart at 5 p.m.
Mhm.
Okay, so please take
Yeah.
it. Yeah.
Or so page 43 is this page. Maybe it's a bit different because I updated from the uploaded version.
So it's time to resume. So whenever Yoshioka-san ready, so please start.
Yes. Yeah, I thought there was another question, and I thought I can answer that during the break session. But if there is, and I would like to take it right now as well, but if there isn't, I would like to proceed. Or
It's
maybe
okay.
you can ask.
It's okay. I'll ask later. You can
Okay,
please.
good.
Thank you.
Thank you. Right, then let me proceed to chapter 4, where we would like to consider more about simulating beyond ground states or beyond toy models and so forth. Okay. So what I mean by algorithmic developments is, what I mean here is that qualitative advancement that allows investigating physics beyond zero temperature and also enhances the flexibility or expressibility of variational ansatz. And it was a bit unclear what is the goal in this direction. I mean, we can consider lots and lots of algorithms. For example, simulate nonlinear equations or other equations as well. But what we want to do in ultimate sense is summarized in this slide. So, I mean, this is a kind of my personal view of what we want to do by making more and more rich neural network simulation techniques. So here, the x-axis is meant to be the real, right-hand side is more real material side, and left-hand side being the abstract one, with the y-axis also added compared to the previous one to denote whether the situation or the system itself is considered in idealized context or not, meaning the existence of thermal bath or impurity or dissipation or so forth. And where we want to go is towards the right upper side of this plane from this lower left side. So here there has already been done, including the initial proposal by Corelli and Troyer about ground states and the quench dynamics in isolated lattice model. And there has been some proposal that would allow us to simulate small molecules in ab initio way. But what we want is to advance and make a progress toward this direction. For example, by considering real solid electronic structure, or consider finite temperature or dissipation effect into the system. And I wouldn't go into like all the algorithms that I consider here, but would like to provide a little bit of picture concerning finite temperature and dissipative system computations. Okay, so in that way, and there has been other advancements as well. For example, initial proposal was starting from RBM, and now we have made the ansatz even more powerful by including it to allow the feed-forward deep neural networks or recurrent neural networks or convolutional neural networks and so on. And we have extended only from the spin models to include fermionic or bosonic systems, or even the composite system of it. And it was, for example, initial one was pure state, meaning the isolated system, but there are also the extension towards mixed states that would include finite temperature or dissipative system, or even allow noisy quantum state that would modelize that realistics in the quantum devices. Okay, And I would like to mention, explain about three, before proceeding to the finite temperature and dissipative one, let me a little bit talk about making more powerful ansatz by combining the knowledge of the conventional condensed matter physics and the neural networks as well. Okay. Yeah, so I misannounced that I would proceed to finite temperature, but first I would start from this direction. Okay, so to say this, I would like to introduce a variational ansatz named the pair product wave function, which was widely used conventionally in VM in the context of variational Monte Carlo, already like from 20 years ago or something. So this one is known to be able to capture the fermionic correlations in a very precise way, but by adding another factor named Gutzwiller factor, which would prohibits double occupancy on the single site, we can also use it to simulate spin systems as well. So, and it was like long investigated by the Imada group, which now moved to the Waseda University, that combining this pair product wave function with the Jastrow factor would allow us to investigate physics in 2D Fermi-Hubbard models that would represent the physics of presumably in cuprets or so forth. So one of the most advanced technique to tackle strongly correlated electrons or spin systems was this pair product plus Jastrow factors, and this is a little bit similar to this Jastrow factor is doing very much similar to what RBMs are doing, in a sense that it would weigh each amplitude in a way in this expression. So given some computational basis sigma, it would return you the weight that is given by two-body Ising interaction like this. So since we have already seen the expression of the restricted Boltzmann machine, we would notice that this is essentially doing the operation of Boltzmann machine without any hidden neurons, but with interaction between the spin sigmas. It was later extended put forward by Nomura and others that we can in fact replace this Jastrow factor by RBMs to incorporate higher order correlations. So we have seen that the physical spins are indeed connected through the hidden spins and introduce higher order correlations. In the paper of Nomura and Imada and others, they compared the simulation accuracy between only using RBM and introducing RBM and pair, and also the behavior of only using pair product with Gutzwiller factors, and have shown that they can systematically improve the accuracy by adding by considering the combination between the RBM and the conventional variational ansatz. So here, green curves are showing the result by this RBM plus pair product, but also by considering the translational symmetry in the system, they can achieve the best performance among the ever considered in the community. Okay, so this gives us this is another way of improving the neural network structures, not only considering the conventional ones or not only including the neural networks, but also in combining the already existing methods would sometimes give better way better accuracy. So as I have already introduced, we can also consider the convolutional neural networks that consist of the local receptors that would extract the feature from the local system. And we have already explained that this shows efficient spreading of quantum entanglement. And this is my personal view, but since CNNs are now simulated heavily using the GPUs, if we want to tackle quantum many-body system in the large-scale limit with existing computational power, then using the CNN could be one of the most promising approaches that in a direction that would not extract physical knowledge so much. So here in the paper of this Liang and others, they showed that the two-dimensional J1, J2 Heisenberg model, which means there's frustration between nearest neighbor and next nearest neighbor interactions, they can simulate the system of 36 by 36, which means it's over 1,000 qubit. But the thing is that they use very heavy computational resource, up to 40 million cores. So I guess this is not available to usual researchers, and could be done only by like large groups or maybe company with huge computational resource. So I guess this is a very one positive news and one negative news. In positive way, we indeed can see that physics agnostic variational ansatz like CNN is outperforming the existing techniques and further showing us the possibility to reach the thermodynamic limit like this. And the negative news is that if we need this much computational resource to run simulation like this, then it would be like the more resource you have, the more you win. So it's a bit kind of uninteresting way of scientific research. So I hope that there would be some compromising point that we can combine the existing technique in an efficient way to reach this kind of system sizes. Yeah, and in their paper they were showing the history of the neural network simulation. So from 2017 to 2020, this year 2022, I think this number of parameter is mistaken because they consider translational symmetry, and it's order of 1,000 here, coming 2 orders larger right now. And I don't know how far we can go, but it's one interesting direction to seek how much resource we can prepare for this kind of quantum simulation and what is the accuracy we can expect from that resource. Okay, yeah, this is a little bit embarrassing. Yeah, so this was about making ansatz more powerful. Now let me proceed, as I promised previously, to finite temperatures and dissipative system simulations, which is concerning my my work a bit. Yeah, so in direction of finite temperature problems, why you want to consider finite temperatures at all? Anyway, so the main reason is that the experimental results we would have is always in the finite temperature. So, and some, for example, in like cold atoms or other system would not allow us to reach to like low enough temperatures. So the ideal thing is to reach that temperature region, but sometimes there would be some limitations in the scope of experimental setups we can have. In that sense, what we want for the theoretical side to have the whole map of the phase diagram or something, and then factor out which regions we are looking at in the simulation, in the experiments. So, and especially for strongly correlated 2D systems, we don't have a very good probe to do that. The tensor network methods are mainly limited to one-dimensional system. There are a few works on 2D, but yeah, it's not as powerful as in 1D. We do have the dynamical mean field theory, which would become exact in infinite dimension, but we know that this is not very quantitative in 2 dimensions. And we would like to propose that neural network would, as we have seen already for ground states, it would provide a strong methodology in case of finite temperature problems as well. How we do this is to use the notion of the purification, meaning that we would first encode a system into enlarged Hilbert space. Here, I don't mean by hidden space, but actually prepare some physical spins that would span the Hilbert space like this. And afterwards, we would trace out this physical state's degrees of freedom, sigma prime, and then obtained the mixed state as the variational ansatz for the thermal equilibrium. How we do this is decomposed in 2 steps. In the first step, we would prepare an infinite temperature state, prepared as a bunch of those states, which couples each physical. And then, starting from this infinite temperature dBm, we would perform the imaginary time evolution as in the ground state problem, and then get the finite temperature state that would correspond to the thermal equilibrium. And in doing these 2 steps, in the second step, we would introduce 2 methods that would give both exact representation and approximated version of the step 2. So in the method 1, what I mean by exact representation is that we would construct a deep Boltzmann machine in which we can compute the action classically efficiently and extract the physical quantity from it. As I have already mentioned, this is not possible to general cases. So beyond that, we are going to introduce the approximation in a numerical way. Okay, so let me proceed to the exact representation. Our observation is that any kind of Hamiltonian can be decomposed such that each operation would be locally operated, let's say for 2 qubits or 3 qubits, whose maximum degree is bounded by the k locality of the Hamiltonian. And once we break up the Hamiltonian into small enough parts, we can encode the operation of this unit imaginary time operator into the parameters like this. So let us consider as an example a case of transverse field Ising model. Here, for example, we consider a one-dimensional case where expression can be also generalized to fully connected Ising model as well. Starting from infinite temperature dBm, we can show that the ZZ interacting term can be encoded by adding hidden spins into the neural network structure. In the second term, corresponding to the transverse field, can be represented by adding another layer of deep neural network in between these existing hidden spins and the physical spins like here. So this is, I think it is more illustrative to look at these graphics. So here, the green ones are for this H1, and both red and green ones are corresponding to represent the H2 actions. We do this again and again to encode the full imaginary time dynamics. So we can grow the network more and more so that at until we reach the target temperature beta. The point is that all the network parameters in this DBM form is going to be real, such that we can do some Monte Carlo simulation for this this DBM to extract the physical quantities, such as the energy or the heat capacity or the susceptibility or so on. By benchmarking on 16-side system, we can show that the net neural network would encode up to the Trotter errors of these physical quantities. So the caveat here is that in order to extract the physical quantities, we need this DBM structure needs to be real valued. So for the Hamiltonian with negative sign problems, we have to do really the negative sign Monte Carlo simulation, and that would not remedy the problem at all. But at least it is very promising that, in a sense, that the existing path integral formalism can be mapped into the language of neural networks. So I've said that system with negative sign problem cannot be done with a method 1, but we have shown that fully frustrated case can be handled by the second method of the numerical approximation. So here, now we are not going to consider the deep Boltzmann machine itself, but keep it to this structure where with 3 layers, with one being the physical spins and another being hidden and the other being the auxiliary degrees of spins. For this one, we use the technique for the grounds, similar to the ground state case, where so it was introduced as the natural gradient, and here I'm denoting as stochastic reconfiguration here. But the thing, or the essence, is that we are going to move the network parameter such that the imaginary time evolution operator would be approximated by this moving delta W. And this delta W could be given by computing the quantum Fisher matrix and also the gradient with respect to each network parameters. We have run this simulation for a 2-dimensional J1, J2 model up to 6x6 lattice, where we could not find any competing result by tensor network or other variational methods. And compared with both the quantum Monte Carlo for J2 equals 0, which is without any sign problem, and J2 equals 0.5, where we can only apply the TPQ method. We can see that the results are in excellent match with the TPQ method for both, and for the 0.5 and also the unfrustrated case as well. For here we, so that computational scaling is a little bit different from what I have previously mentioned. And here, for this case, the sampling, Monte Carlo sampling part was more dominant compared to the parameter update. So the scaling was observed empirically as this form, where n being the number of sites and nh being the hidden spins. And actually, we're taking the number of hidden spins to be nearly equal to the number of sites. So practically, it was n cubed in our case. So this gives us strong advancement of neural network calculations for exploring exotic physics. So the mixed state calculations is not only limited to the finite temperatures, but it can also include open quantum systems, which would also include dissipation effect or interaction with the heat bath or those stuffs. Here, open quantum systems mean that your target system, which is intended to be usually microscopic and coherent, is interacting with the external environment, which is usually macroscopic and behaving like heat bath, such that by tracing out this environment would leave us with a quantum master equation that is no longer showing unitary dynamics as before. Here, so as a most simplest case, we are going to consider the case of quantum master equation with both CPTP and Markovianity. And the nice point of this type, also referred to as the Lindblad equation, is that they would be assured to have the steady state if all the Hamiltonian, also the dissipators, are time independent. So here, let us further look into this equation in case that there are audience that are not familiar with quantum master equation. So here the time derivative of the target density matrix is given by this super operator, which is explicitly given by sum over the unitary dynamics and the dissipation over on the density matrix here. And the operation of the dissipation is more in detail given by this form, where gamma could be sigma minus in case of damping or so forth. If we want to solve this kind of equation, and for example, in the case of steady case, what we do is to vectorize the master equation so that we can capture the quantum state in the language of the pure state neural networks. So here, it is graphically clear that what we have done is to rewrite the matrix in terms of vector like this, so that also the operation of the Levelian becomes a matrix instead of the super operation. And when we want the steady state to be specific, we can find the ground state in a sense of this L dagger L operator instead of considering the L itself. So the spectrum of this Levelian would be schematically given like this, where, if I have mentioned, it is always assured to have the steady state as a zero eigenstate with this operator. And this becomes a real non-negative spectrum when we consider the L dagger L with this 0.0 eigenstate staying as where it was. Of course, if we want to consider the dynamics, then we can do the similar stuff for the time-dependent case in the pure state, meaning that we can also consider another type of variational principle and move the parameters accordingly. But in case of the steady state, we can see that we can simply use the technique of ground state simulation to reach the state. So since So once you have defined the cost function, you can simply run the optimization as is and get simulate this the system as we want. In our demonstration, we have considered both 1D and 2-dimensional system of a transverse field Ising model with a damping effect, meaning that the gamma in the previous slide is now denoted by sigma I. So we have performed simulations for 16 sites for 1D and for 25 system size for 2-dimensional system, and we have demonstrated good agreement with exact or the biggest ever variational simulations. And what was surprising, which was pointed out by simultaneously published paper by Hartman and Carlile, was that this region, although it seems to be very weakly entangled, the number of parameters was quite large in the MPS simulation, meaning that considering the vectorized simulation using MPS instead of the density matrix simulation by MPO. So now with this technique, we also would like to propose that the 2-dimensional open quantum many-body physics are ready to be hunted using the neural network states as well. Okay, so up to now, we have considered the forward probe mainly about the variational calculation, but there are also another possibility of encoding quantum states into neural networks, which is the inverse problem. And this has been called the quantum state tomography in the context of quantum information. So let me proceed to explain what is done here and what is the motivation about doing this. Okay, so the notion of quantum state tomography is could be expressed in terms of machine learning as unsupervised learning in various measurement bases using single quantum state. To understand this statement or the connection, I think it is more instructive to start from what I mean by unsupervised learning on probability distributions. So here it is like what we want to do is to know what was the underlying probability distribution P of X from using the data points Xi, which is unbiasedly sampled from this P of X. And what we can do is to prepare some variational ansatz parameterized by this theta and fit into this data points. And how we do that is there's a lot of ways to do that, but one representative would be to employ the maximum likelihood estimate, which optimize the theta so that this likelihood function defined as the product over this quantity would be maximized. So of course we can do this theoretically, but when we want to do this for neural network, we find out, for example, with a Boltzmann machine, that we need this kind of gradient calculations, where so when we want to optimize the likelihood with respect to the parameter W, the interaction, then what we need is the mean value of Xi times Hj for with the probability distribution corresponding to the actual model and also the data. So it is very easy to compute the second term from the data if the data size is not very big. But for this first term, we need exponential cost if we want to do it analytically. So in reality, we are going to replace this with Monte Carlo evaluation. So the schematic for doing unsupervised learning would be this kind What we really want is this P of X, the target distribution, but we assume that we cannot have the exact expression itself. And what we have is only the data points sample from the target. It would be the best if we can fit or optimize all the parameters straightforwardly to explain these data points, but even that is computationally costly. So what we do is to do Monte Carlo sampling such that the distribution of these data points is going to resemble that of the data points. Okay, so since this schematics has been given, now I think we are ready to proceed to the concept of the quantum tomography, in which we are going to consider multiple measurement bases. So let's consider an n-qubit system, which means that for each qubit, we would have a degrees of freedom of XYZ measurement bases. If we really want to do the full tomography, then what we do is to do the measurement as many as possible for all the measurement bases. So obviously, this is going to require us exponentially many sampling cost. But here, what we would consider is to assume that the number of these samples are limited. And also, we want to do this using limited classical computational cost. So the best way known so far to do this is to use the variational ansatz, which would at least allow us to do this fitting with polynomial cost with respect to the number of the parameters. Okay, so the schematics are now replaced here by unknown target state, from which we do some quantum measurement and get the probability distribution or the data corresponding to the measurement. And here as well, we cannot do the direct fitting into this probability distribution. So we would consider so that the sampling from this ansatz at each measurement basis is going to resemble the data points you would have. So this is like considering the Kullback library divergence as a sum over many measurement bases. Okay. So this scheme was first proposed by Giacomo Torlai and others in the paper of this 2018, and they showed that the W state represented as this form, up to 80 qubits, can be readily done. We can do the tomography if we really using this RBM states. So in other words, we have already seen that we can construct exact expression of W states with order linear and parameter hidden spins. So this would make us expect that also the tomography can be done by relatively low cost with high fidelity. They also added some random phase into the W state, meaning that for each computational basis here, they added some random phase, and also showed that the complex phase can be extracted as precisely, not as the amplitude itself, but near quite in a good agreement. Okay. They also did tomography not for the quantum information related field, but also for the ground state of quantum many-body states. So here they considered 2D transverse field Ising model of over 100 qubits, and also the XXZ model of over 100 qubits, and showed that the magnetization is well captured by this tomography. And so here it is, they're showing the result for 2D structure for local physical observables, but they also did the tomography and computed the entanglement entropy, which is a global quantity for a 20 qubit system. and verified the agreement is very good. Okay, so it seems that the tomography direction is very good, seem to be very promising, and there has been some extensions to mixed states or using more efficiently sampling generative models. But there were some counter arguments that this kind of shadow tomography on quantum observables can be better done by randomized measurement rather than doing this kind of classical post-processing. So unless you're interested in like doing some post-processing, like computing entanglement entropy or doing some error mitigation, it is better, you would better use the other kind of measurement scheme in my point of view. Okay, so this is it for the chapter 4, and I think there is no much time to talk about chapter 5, which is a little bit off the topic from today's talk. So I would rather, wrap up today's talk and start taking questions. Okay, thank you.
Yeah, thank you very much, Yoshioka-san. So we have some time. So for audience, could you, okay, Ono-san, raise hand. So please.
Oh, yes, thank you. Thank you for very nice talk. I have a question about final temperature problem.
Yeah.
So I think you construct the pure state of finite temperature system, right? So is it possible to construct density matrix for this system?
Yes. So actually what we were doing is the constructing the density matrix. So what we have done is to enlarge the Hilbert space. Let's say there's 10 qubit. And what we actually did was to encode a system into 20 qubit system. But we optimized the parameters so that by tracing out this sigma prime degrees of freedom, we would obtain the density matrix corresponding to the Gibbs state. So we were doing the simulation of pure states, but effectively encoding all the information of the density matrix.
Oh, I see. I see. Okay, I see. I see.
Yeah.
I got it. Yeah, thank you.
So if there are any questions? So I have one question. So could you please just comment about fermionic system? So what is difficult things to applicate machine learning techniques into fermionic model? So
yes. So
yeah.
Okay. Yes. So there are multiple directions to encode fermionic systems. And indeed, I have also worked on encoding fermions as well. So one way is to use the combine the technique of the existing fermionic systems. So here I introduce this pair product wave function to be applied to spin systems. But if we relax this Guth-Wheeler factor, not to fully prohibit double occupancy, but to like partially prohibit by making this exponential over something, then it would not completely rule out the double occupancy, which would allow you to tackle fermionic systems. So, for example, this means that this pair product is capable of fermionic systems, and also by combining this pair product with this Jastrow wave functions, or RPMs, would allow you to simulate fermionic systems. And in their paper, they indeed simulated the fermionic system using this technique. So yeah, by relaxing this occupancy condition, this ansatz would allow you to have fermionic degrees of freedom. So that's going to allow you one simulation way. And that's one way. And another way of dealing fermionic system is to really encode the fermions into spins so that all the spin techniques can be used. So so maybe Sakurai-san is familiar with this, but one way of doing that is to use Jordan-Wigner transformation or other fermion-qubit mapping techniques, so that all the Hamiltonian terms would be expressed using qubit terms. In that context, we can use the RBM for spin systems and simulate the ground state. I mean, it has all the same property, except that the pop-in terms would have Z strings in between. But yeah, in principle, you can use it. And also, there's another way which came out in my mind, is to use the recurrent neural networks, since it would remember all the, since it is giving you the conditional amplitude, it would be also possible to give you about the antisymmetric sign structure as well. So you can also, I think you can also do that, but I think there's no work concerning fermions using RNNs.
Yeah, it's interesting. So there are many things to do in fermionic systems.
Yeah.
So, okay, thank you. So, is there? Yeah, sure.
I've got more of a quantum information background. I'm just a bachelor student. So my question was about slide 51, in which you said that the good news was that we could use quantum neural network to to get the order of √n. But to actually do this, we would need to use 40 million cores. As a quantum information with a background, that's something like, if we could actually do all of this with convolutional neural networks, so we wouldn't actually need quantum computers, do you think? Or would we still need them?
Yeah, I think we still need them. I mean, this is a point. So J1, J2 is indeed very difficult problem with detailed structure, but we still have lots of harder hierarchy that we still do not know. And I would say that convolutional neural networks are very good with this spin models, but for the fermionic models, it's even like 100 qubit system we cannot tackle with neural networks yet. I think I did simulation myself, and for example, for the ab initio molecule calculations, 50 qubit was already hard. So it really depends on what kind of problems you would consider, which size you can go. And for example, so in the case of 1D, where we know already that it is classically simulatable, MPS simulation can go up to like 1,000 or 10,000 qubits sometimes. But, and yeah, so it could happen that if the ansatz is a very good connection with the problem instance, you can go to very high problems and very big simulations. But the point is that for MPS, we know that what kind of condition would allow us to go into larger sizes, while for the neural networks, we do not know whether that holds or not. So, and computational complexity would tell us that it is not like capable of all the systems. So I believe that some sort of important questions can be addressed by neural networks, but there would be much more remains that should be more handled using quantum computers.
So because I know how hard quantum computers are to make and to do anything reasonably good with them, according to the fault tolerance, the error correcting codes we've made, the overhead is so much that we will actually use million physical qubits to actually get to, reasonable amount of logical qubits. So my question would be, suppose we actually get the overhead very less and we're actually able to simulate 1 million logical qubits, then wouldn't all of this, what we're actually trying to do here, would be not needed? Is that true?
It's difficult to foresee that because by native, quantum computers are better at simulating dynamics, and also quantum simulators are good at simulating dynamics, where classical simulators are good at like simulating ground state properties or eigenstate problems. So yeah, I think, yeah, even if you use phase estimation, which would give you the ground like eigenstate calculation, yeah, I'm definitely confident that dynamics would be like the first quantum advantage we can see. But for the ground state, I think it is unclear at the current point. Yeah, I mean, even if,
I do think
that's a very good question.
Yeah, and I do think that getting to fault tolerant quantum computer is going to be way harder. And in the meantime, even if they are like jack of all trades and can do everything, still in the meantime, doing this will actually allow us to probably build quantum computers faster. Or when we actually have the quantum hardware, we'll actually be able to do some kind of neural networks that are not even possible today.
Yeah, right. Okay, so by saying kind of neural networks, it depends on whether you want to do this kind of quantum many-body simulation or actually do the quantum machine learning. And my personal view is that I think in quantum computers, it's better not to mimic the classical algorithms so much. I mean, maybe you know that quantum algorithms are now like getting more and more unified to rely on single subroutine of the qubitization or the QSVT. So I have seen that many algorithms are rather like the quantum speedups are rather based on this single algorithm. So I think that I think even if you have the complete quantum computers, I would say it's not like quantum neural networks, which people are like advertising for some reason, but it would be like truly quantum native algorithm that would be implemented. That's
So basically what you're trying to say that even if we have a quantum computer, it won't be jack of all trades. We'll still have classical computer in some domains that will outperform quantum computer easily.
yeah,
right?
yeah, of course. I think that is very
I actually
clear right
agree
now.
with that. I actually agree with that because the hype is too much. They actually say everything. They hype it too much. I know that.
Yeah, that's true.
Thank you very much.
Yeah,
Arigato.
thank you very much.
And Kamiya-san, please.
Yes.
Question, please.
I'm not sure if the time allows me to ask some question. Thank you for the wonderful lecture. So I have a question about the simulation for flat system. I think it was a J1, J2 model at finite temperature. So you talk about some method that the detail of which I'm not familiar with. So could you go through about it, once again slowly?
Yeah. So this is a imaginary time evolution algorithm that would yeah, I'm not sure if it's familiar with the path integral, but that the overall idea is shared among each other in a sense that in both we want to start from the infinite temperature state and gradually go down to zero temperature state via imaginary time evolution. And did you mean by the method 1 or 2, or did you mean this overall picture?
No, I'm talking about some method to deal with time problem. So you mentioned that even with this method, there's some difficulty associated with the model with QMC time problem, and then you introduce some trick to you can say partially resolve that problem. So I was interested in that.
Okay, yes, yeah, that was a misleading statement in a sense that sorry, yeah, so it's similar in a sense that VMC would like formally seem to avoid sign problem, but actually not. It's very similar to that. So VMC indeed is going to perform sampling based on psi squared. So it does not have the sign problem itself, but practically when the sign problems are stronger, then the sampling complexity, not complexity, but sampling number you would need is going to get higher and higher. So that kind of hidden dependence on the sampling number or the variational parameter is still present in this method as well.
I see. But I was wondering about this so-called Fubini study metric. What is this?
Okay, so Fubini study metric is like the metric between quantum states. Yeah. And it is like it is the arc cosine between the overlap of states. And it has been known that this kind of metric would give you the most efficient way of evaluating the quantum states with each other. I mean,
Can we think of this a kind of reweighting from original weight to somehow modified weight?
The weight. You mean weights? Yeah, the network parameters are modified such that the operations are approximated. So in a sense that the network weights are like reweighted.
I see.
But,
I see.
Yeah, but I think it's different from the reweighting technique that Monte Carlo people are discussing.
I see. So my last question is the following. So in this kind of, how can I say, I shouldn't call this reweighting, but you should call this arc cosine or something, right? So are there any possibilities that the wave function, the exact one and the approximate one, they have increasingly small overlap between them, so that the simulation becomes practically very difficult? Do you expect this kind of difficulty?
Okay. Yeah, that could be possible. Yes. And yes, this metric, the difference between this approximate and exact is going to be proportional to delta t. So time step is going to play a big role here.
Okay.
So by taking this parameter update to be the optimal value, this this difference would be delta t squared. So if you know that you're getting into very difficult regime, then what you would practically do is to set this time step smaller.
I see.
And there is a possibility that like in close to the phase transition point, this delta t would explode with respect to the system size. And that is like the fundamental limitation of imaginary time evolution, I guess.
I see. Thank you. I will take a look into these papers. Thank you so much.
Oh, thank you.